Good afternoon, ladies and gentlemen, and welcome to this afternoon session on hybrid AC/DC microgrids for residential applications. In today's program, we're going to be taking a look at the Purdue DC Microgrid House Pilot Program and a little bit about the Emerge Alliance Residential Nanogrid Technical Standards Committee. Our presenters today, primarily, I'll have a few words to say, but our real stars are Doug Hamborski, an architect from Hamborski Solutions Group, and Jonathan Orr, a PhD candidate who's leading a lot of the research for the DC Nanogrid House up at Purdue University. And of course, myself, Brian Patterson, I'm the chair of Emerge Alliance, which is an open industry association with members that represent industry and academia and government agencies and other associations. We sort of collaborate with a lot of folks across the industry. And next slide, if you would. What we do at Emerge is really we're developing Vanguard standards systems for hybrid AC/DC microgrids and DC microgrids. We started out with DC, but as most people know, pretty much all microgrids are actually hybrids between AC and DC. And we try to do leading edge kind of standardization in advance of the market developing. Most traditional groups wait until the market develops a little bit more. We're trying to get in front of it. We also do a lot of market development, mostly through education and technology demonstrations. And of course, one of the reasons we're here at North American Smart Energy Week is because we partnered with SIA and SEPA, the two organizations that sponsor this event, in providing some of this education and demonstration work. The end game for us at Emerge really is to see if we can move the ball forward on providing a new digital-based energy network. We like to think of it as an energy network, an internet, or a grid of grids. And we think we're at the crossroads for whether we stay with the traditional sort of unidirectional grid that currently exists, or whether we move to a more mesh network topology, where we have distributed intelligence and distributed resources combining to provide a more resilient and reliable power network as the market expands in electricity. So without further ado, I'm going to turn the presentation over to Jonathan Orr from Purdue. Jonathan?
Thanks, Brian. Really appreciate that introduction. So, hi everybody. Thanks again for coming to our session here on microgrids. And again, my name is Jonathan Orr. I'm a PhD candidate here at Purdue University, and we are working on a project here that we call the Purdue DC House Nanogrid project. And a nanogrid in this case is a specific application of the microgrid, in which we are actually trying to implement kind of hybrid DC-AC network inside of a residential home. So as you can see here, the Nanogrid House project is a culmination of a multitude of different aspects. We are working with the power grid and utility companies to make sure that from a technical side and a utility side that we're aligned. We're looking at the home as a whole, not just from electricity aspects, but also from energy improvements. We're looking at trying to retrofit existing equipment to make it work with DC to better align with the nanogrid itself. Coming up with a novel nanogrid design that could be replicated in other homes. And also, in addition to the energy, building a smart grid network and trying to understand how the house reacts to different circumstances, conditions, environmental settings, and the residents' usage characteristics inside the house. Next. Next slide. Yep, perfect. So this is the DC house in all its glory. It's a 2-story residential home based in West Lafayette, Indiana. It was built in the 1920s, so it has a lot of history and a lot of character, and a lot of improvements that needed made. And there's actually 3 graduate students that live and work inside the house full time. So it's a real environment. It's not artificial. There's real people living there using real utilities and appliances. So this is a perfect environment and almost playground for us to to test out a nanogrid setting like this. Next slide. So inside the house, we have instrumented all of the existing AC circuits through the help of Eaton with their EMCB Wi-Fi circuit breaker modules, and another system called the TED Pro Home modules, which allow us to collect electrical and energy data from all the different devices and circuits in the house on a minutely basis. So we can get real-time feedback of what's going on from the AC side, and subsequently with the DC side once we finish implementing the nanogrid. Next slide. So this is our goal here. We're here on the left right now with our with the existing structure. We're bringing in solar. We have a battery. We've got the typical utility coming in through a normal AC load panel. The problem is that anytime we want to use DC-based loads, we have to go through all these conversion steps. And there's a double penalty involved when you add solar or wind into the mix. You throw solar up on your roof, then you've got to convert the solar from DC to AC to be used within your home. But then at the point of use in many different loads like LED lights, computers, TVs, and all kinds of different things, then you got to convert back again from AC to DC. So our goal is over here on the right. We want to have one central inverter at the front of the home and have a universal DC bus running through the house, which allows us to minimize those AC to DC conversion losses and have much higher efficiency DC to DC conversions, which we know we can get to a much higher level. And of course, we know that some loads will need to continue using AC, so we have support for that as well. And this slide shows you the actual implementation of what that looks like. So our nanogrid is composed of several pieces of equipment. We have a bidirectional inverter at the front with isolation transformers into input and output from that inverter. We have a DC-DC converter module, which connects up to our solar panels. We have a 14.3 kilowatt installation on the house's roof. The DC-DC converter also has multi-power point tracking built in, and it helps regulate our 380 volt DC bus, which constitutes the backbone of our nanogrid. Then we also have a 21 kilowatt hour battery system connected on the DC side to help us store some energy for later use and even function in an island mode independently from the grid. And in addition to all of that, we have a low voltage, what we call the LVDC side of the grid, which runs about 48 volts DC for use with smaller applications, smaller devices, and is also touch safe for the residents to be around. Yep, next slide, please. This is our electrical schematics of what you just saw there from that top level diagram built in. So our goal with this was to make it very flexible. Again, this nanogrid that we've constructed inside the home, it has the flexibility to support not just DC loads, but also AC loads, which is the perfect environment for us to run comparisons between AC and DC retrofitted devices and evaluate and compare their performance and see what kind of efficiency savings we can actually gain from doing that retrofit operation. Next slide. This is a top view level of our home. You can see our solar guys there working on the roof. This was back earlier in February of this year that we finished the solar installation up there. So, and these guys have some outstanding software that called Helios, which actually lets us estimate throughout the year based on the environmental conditions and the physical location of the panels and the angle and all of that, exactly how much energy we can expect to produce each month. So unfortunately, we do live in West Lafayette, Indiana. It does get pretty cold, and some of you guys may remember last year we had a particularly cold winter, the polar vortex of 2019. We actually expended over 2 megawatt hours of energy from the heat pump system alone, just trying to heat the house. So we know that the solar will not be able to completely make the house energy independent, but especially during some of the summer months when the energy loads are lower, we definitely think we can get maybe a week or even more of the house running in a standalone mode. So that is definitely one of our big goals. Next slide. So we also have a bunch of dashboards and visualizations that are hooked up to our energy monitoring circuits so that we can watch these things in real time and also go back and do a thorough analysis and look at the typical usage conditions of various appliances and equipment that we have in the house. We can see the times of day when there's peak load. We can check out maximum power use and instantaneous power use at different times of the day. So all different things like that are critical and essential to helping us design the nanogrid. So with that in mind, in particular for the, next slide, for looking at types of equipment that we can retrofit in order to see a real benefit from running a DC grid. The first thing, of course, we looked at is a heat pump. So we know that in the US, heat pumps, they can use up to, heating and cooling alone can run you about 50% of your energy costs throughout the year. And on this left side of this slide, you show like a typical conversion from an AC input to a controlled AC output that would run a motor in a heat pump type of device. What we want to do is bypass the AC input and the rectification, power factor correction, all of those input stages, and just directly feed DC into the heat pump directly into its control circuits. So in doing so, we believe that we can save a non-trivial amount of energy in the long run, especially when you consider that 50% of those energy costs come from this thing alone. So if you can save a few percent from avoiding conversion losses, that can add up in a big way over the course of the year. So on the next slide, here I've shown you a picture of our psychrometric chambers here at Purdue University. We have a 500 volt DC 15 kilowatt power supply and a train heat pump unit, which they have very graciously retrofitted with us to consume direct DC power, which is awesome. So we have this thing set up in our psychrometric chambers. We can test it with all kinds of different environmental conditions, both indoor and outdoor. One of our texts down there in the bottom left, you can see is showing you that our chambers go down from -4 degrees Celsius all the way up to 130 degrees Fahrenheit. So we can test a huge variety of different conditions. But again, this is a great opportunity to compare the DC performance on the 380 volts compared to the typical AC performance at the house, which is using split phase 240 volts AC. And then on the next slide, this is a inside look inside the psychrometric chambers of the indoor and the outdoor unit comprising the heat pump, showing you all of the different sensors that we have hooked up to this and things that we can monitor and collect. And on the following slide, we summarize the AC testing that we've done with an unmodified heat pump unit and the DC testing that we've done with that heat pump that we showed you previously that's been retrofitted for DC. So far, what we have seen between data collected from the house compared to the DC experiments that we've run at the psychrometric chambers is about a 3 to 7% improvement in terms of energy efficiency. So again, not too bad when you compare that to your 50% of your energy costs for the whole year. 3 to 7% can make up quite a bit. So definitely more to come on that. Following the heat pump studies, we've also been doing a lot of work surrounding energy improvements with the house itself, because ultimately all of these different things, the nanogrid even, although it's electrical focused, I mean, our ultimate goal here is to achieve improved energy efficiency. That's our goal. So throughout the lifetime of the house, we've made a number of different improvements, ranging from installing a variable speed heat pump, installing insulation, replacing windows with high efficiency, insulated windows, different things like that. And what we've done is we've measured the energy consumption, particularly from the heat pump for heating and cooling of that space, compared to the weather conditions outside. And what that allows us to do is determine like a system effectiveness. So if it's 20 degrees Fahrenheit outside and we'd like the house to be at this like 65-degree Fahrenheit balance point, how effectively is the heat pump heating in that specific circumstance? And that's what you see on this graph is a plot of the cooling shown in the blue and the heating, the hourly heating cost shown in the orange yellow color there. And obviously, again, we're in Indiana, so there's a lot more in the orange than there is in the blue. On the next slide, what we do is we take that environmental amount of heating and cooling required compared to the actual energy that was expended by the heat pump for heating and cooling, and overlay them on each other. And it follows pretty well. You can see that the temperature compared to the energy consumption is pretty well in line. But again, what we're really interested in is these big spikes, like how well the heat pump performs there. And again, you can see in January 2019, there's the January, February, there's some big spikes, and that was during the polar vortex. But on the last slide of that testing here, you can see our overall heating and cooling system effectiveness. And again, this is pre-DC. This is just energy improvements that we've made in the house itself. You can see that we've achieved pretty substantial improvements over the course of the different renovations that we've applied to the house. Again, all seeking the goal of energy independence and energy efficiency. On the next slide, here I show you the smart network aspect of the house. So you can't have DC without lots of different sensors, and that's exactly what we're after here. We have implemented a whole home smart network in which we monitor virtually every parameter we can get our hands on, not just energy, but also room by room environmental conditions, like the temperature, like the humidity, like the airflow, how much light there is in the room, the air quality, anything that we can. And we're trying to then take that and use it for feedback to control different devices. So if we know a room's not occupied, then stop heating it. If there's too much light in the room, then dim the lights, things like that, that we can use directly to help save additional energy. But the great thing about these devices is they can run on this fantastic technology called Power over Ethernet. Power over Ethernet runs at 48 volts DC, which is on our low voltage DC bus. And that PoE line, which is just simply an Ethernet, like a Cat5 Ethernet cable you probably have plugged into your computer right now, that can serve up to almost 100 watts of power. It's pretty incredible. So that is running around the entire house, and it's powering all of our sensors, which is collecting all this great data and letting us control our appliances and devices. And on the next slide, here you can see this is a simple implementation here that we have in our dining room. We're using Raspberry Pis, ESPs, Arduinos, all kinds of very low-cost microcontrollers and sensor arrays to gather all of this data. And then, like the energy dashboards, we also have dashboards and visualizations to help display this data and show us what's going on. So that's what we're doing here at the DC house. I will now hand it over to my co-presenter, Doug, and let him talk a little bit about some other items. Thank you.
Thanks, Jonathan. It's exciting as an architect and someone who's been involved with eMERGE for probably around 10 years now to see your team developing the sandbox, finding real-world applications for all these great emerging technologies. With that as an umbrella, the eMERGE Alliance has put together a variety of committees to define and create standards for these emerging technologies that utilize direct current DC power. One of them, Jonathan and I co-chair, it's called the eMERGE Alliance Residential Nanogrid Technical Standards Committee. And in essence, the mission of this committee is to develop standards for DC and hybrid, that's very important, hybrid AC-DC power utilization within a nanogrid configuration for residential use buildings and loads. Also to promote the development of DC-powered products to be used in residential applications. Provide technical resources to the design community for the DC-based technology for residential applications. In essence, emerge and we see a future where the house is really going to become a DC powered house, and we're going to try our best to facilitate developing standards to make that a reality. So the outline of what the committee is going to be doing is we're going to have a hybrid use of AC and DC power, sort of look at that, define it, define the different interfaces between AC and DC. There's a variety of power sources for both AC and DC. How all these things will connect together, power distribution, both AC and DC, whole house subsystem topologies, sort of a vague term, but there's all these little subsystems within the overall network of power, as Jonathan went over, from communications to power to control. There's all sorts of smaller systems within the overall system. Operational criteria for appliance and device loads for manufacturers to develop their products around. Control options, there's lots of control needed and utilized in these newer smart homes. And a transformative path to implementation. We're not just going to flip a switch and one day, oh, there's the DC house. It's going to evolve over time, and this committee is hoping to help to assist with the transformation. On the power side of what the committee will be looking at is a wide variety of DC sources, from AC to DC rectifiers. Of course, PV solar is one of the dominant DC sources in the industry or in the market today. Fuel cells, wind, ISP, microgrid, the list as shown. The AC sources, of course, the dominant source is the good old-fashioned utility grid. Been with us for many decades, did over a century now. And DC to AC inverters. You know, we're coming to a time where maybe your community power isn't going to come from an AC grid. Maybe it's going to come from a community DC source, like a solar farm or something of that nature. But you still need to run an AC device in your house for some period of time. So you'll have DC to AC inverters the way you have AC to DC rectifiers or power supplies. And then, of course, the missing link is energy storage. And there's a variety of chemistries and technologies evolving to support the storage industry. As far as the loads, there's a list of loads in your house as we speak. The issue is that as we evolve in our technology, the goal is that more and more of these loads will be powered by direct current power as opposed to AC power. And in fact, most of these loads are already internally DC, and they have, as Jonathan pointed out, these power converters or power supplies within them. We hope to eliminate that, go direct to the DC portion of the load and eliminate that. This committee is sort of, I call it 2.0, but eMERGE launched the residential committee many years ago. I was involved with it at that time. And so this is really the Resi and Nanogrid 2.0. And so we have a framework of data and information that we have from previous efforts that will help us move this committee along a bit faster. One of the things, since nanogrid wound up in the committee's name, we kind of said, well, what is a nanogrid? And it has many different definitions. We're not going to present it on this presentation because it's going to be part of the work of this committee. But it's an important word, and it's going to become more and more relevant as we head into power networking between microgrids, nanogrids. And so this slide is representing that it's not a one-size-fits-all, and we're going to help define that in our committee for the purpose of our committee. The other big issue is hybrid house. It's in this presentation's name. The Purdue house is a hybrid house. And we acknowledge in this transformative period of time that we're in, we're going to have AC/DC houses. And so it's going to be important for these houses to accommodate either or both AC and DC, from power sources, from grid power, the the different sources and the different loads. What's going to define the need is the load. Is it a hair dryer? Is it an appliance? Is it a TV? Is it electronics? And then the house will be designed and distribution established to support those loads. And over time, the loads will become more and more key to DC. So here's just sort of a quick graphic of how a hybrid house would have a variety of sources coming in, and then within the house, of course, it'll be subdivided into those smaller networks of AC and DC power. So I'm going to hand this now back to Brian to just close out with some more eMERGE news. And in the absence of Brian, let me point out that in addition to the residential committee that Jonathan and I are involved with, the eMERGE Alliance is really at the forefront of developing technologies and information and standards for supporting the entire evolution of really the use of direct current power and hybrid power, essentially all tying to the highest efficiency available in the marketplace. So if you
Doug, I made the classic mistake of going on mute while you were talking before. But in any case,
go ahead.
Doug is pointing out that the various committees at the nanogrid level really consummate or connect together in what we call the grid of grids or community microgrid work that we are starting to do at this point. Again, the end game is to have a mesh network connectivity between all these resources, distributed energy and distributed intelligence, working on a holonic platform. In other words, that individual nanogrids can operate either independently by themselves or collectively in a system that becomes collaborative, if you will, or supportive of each other in a community, and then rolling up to the national grid or regional grids. So we're working at all those levels. And there are pilots now underway, probably one of the more notable ones that are using this 3 or 4 tier grid of grids approach is at the Kirkland Air Force Base in Albuquerque, New Mexico. We'll be talking about that in one of the other presentations. But suffice it to say that we're not just looking at one application. If you've seen one nanogrid or one microgrid, you've just seen one microgrid. We're looking at all the different applications for microgrids and how they come together in a self-aware neural network topology that is capable of being highly resilient and self-healing and collaborative to reduce cost and to provide the highest levels of reliability and resiliency in the system. The next slide, if you will. So that does conclude our presentation, but if you want to contact any of us, we are using eMERGE organization addresses. So Doug, Jonathan, myself, all available through one of these addresses. So thank you very much, and thank you to our 2 speakers today, Doug Hamborski and Jonathan Orr. And hopefully you'll get an opportunity to see more about the Purdue House as it progresses. Thank you and have a great day.